Antiparticles and neutrinos. In this third elementary particle physics video, we will study what particles and antiparticles are, and we will also study the neutrinos, often called ghost particles because they barely interact with anything else. Thanks in advance for watching this video. If you like this video, don't forget to like and subscribe to the channel and activate the bell. It is very important for the continuity of this channel. All matter particles, such as electrons, protons, and neutrons, have antimatter counterparts, positrons, antiprotons, and antineutrons. Particles are identical to their matter counterpart, but with the opposite charge, and other quantum numbers are also reversed. In 1998, English physicist Paul Dirac developed a relativistic generalization of Schrödinger's equation for the electron. The energy of a relativistic particle is given by equation, from which we can write. As we can see, this equation included solutions with both signs. In the late 1940s, with the development of quantum electrodynamics by Feynman and others, the negative energy solutions of the Dirac equation were re-expressed as positive energy solutions of a new particle, the positron. Quantum electrodynamics, whose predictions have been verified, requires that every particle must have a corresponding antiparticle with the same mass but opposite electric charge. A collision between any particle and its antiparticle partner is known to lead to their mutual annihilation. Annihilation is the process that occurs when a particle meets its equivalent antiparticle. They both are destroyed and their mass is converted into energy in the form of two gamma-ray photons. Pair production is the opposite of annihilation. Pair production occurs when the energy of the photon is used to create a particle-antiparticle pair. In order to produce a pair, the incident photon must have energy at least equal to the rest energy of the particles produced. Antimatter creation occurs naturally in high-energy processes, involving cosmic rays and high-energy experiments in accelerators on Earth. Let's see how creation of pairs and annihilation work for electron-positron. While a high-energy photon passes close sufficiently to a heavy nucleus, the photon disappears and its energy reappears in the form of an electron and a positron. For this reaction to take place, the incident photon must have at least 2 times the electron rest energy, as displayed in the next figure. This transformation of energy into mass must take place near a particle, such as a nucleus, to conserve momentum. The kinetic energy of the recoiling nucleus is extremely small. Thus, all of the photon's energy, which is in excess of which required to supply the mass of the pair, appears as the kinetic energy of the pair. The positron interacts along with other electrons and loses energy through ionizing them. It will combine with an electron and annihilation occurs, resulting in the complete conservation of their rest mass to pure energy in the form of 2 oppositely directed gamma-ray photons. Let's see how it works. Pair production can only occur if the incident photon has enough energy to account for the rest energy of the two particles created. In short, the incident photon must have at least 2 times the electron rest energy. To calculate this energy, we use Einstein's equation. To solve item B, we use Planck's equation. The inverse of pair production is called pair annihilation. It occurs when a positron and an electron collide. Before drawing the Feynman diagram for annihilation, we should recall that interactions occur at the vertices, and the vertices must have 2 straight lines connected to a third wave line. So the electron emits a photon and becomes a virtual electron. This virtual electron then annihilates with the positron with the emission further photon. The antiparticles are usually named by placing anti before the particle's name, with the exception of the anti-electron, which is usually called the positron. The symbol for antiparticles is usually the same as the symbol used for the particle itself, except it has a bar over the top of it. An exception to this general rule is the positron, which is usually uses a plus sign. Other exceptions include the particle-antiparticle pairs for muons, pions, and kaons. Before discussing beta decay, it is better to define what is meant by decay in particle physics. In nuclear physics, nuclear decay means that an unstable atomic nucleus is transformed into a lighter nucleus, accompanied by the emission of particles or radiation. For example, a typical alpha decay reaction is the conversion of uranium-238 to thorium. But in particle physics, particle decay is the spontaneous process of one unstable subatomic particle transforming into multiple other particles. This type of decay is strange because the end products are not pieces of the starting particle, but totally new particles. The particles created in this process must be less massive than the original, although the total mass energy of the system must be conserved. A version of the weak force was first described in 1933 by Enrico Fermi while he was trying to explain beta decay. In the decay process, a neutron is transformed into a proton with the emission of an electron or beta particle. Fermi considered that beta decay could not be explained by the strong nuclear force because this force does not affect electrons. It could not be explained by the electromagnetic force because this does not affect neutrons. And the force of gravity is far too weak to be responsible. The existence of beta decay indicates that there must be another interaction, the weak nuclear force acting in the nucleus. This second type of nuclear force is much weaker than the strong nuclear force. To better explain what happens in beta decay, we need to understand what a neutron is made of. A neutron is not made up of a proton plus an electron plus a neutrino. A neutron is made up of 3 quarks, and a proton is made up of 3 quarks as well. When a neutron is hidden in an atomic nucleus, it is extremely stable and does not decay because the quarks are squeezed very tightly to each other. So the neutron mainly feels the strong nuclear force, and the weak nuclear force of quarks will not play the main role. But when conditions are right, as in neutron-rich atomic nuclei, the nuclei become unstable, and this unstable situation allows the weak force will play the major role to convert down quarks into up quarks. Feynman diagram of beta-minus decay is given below. If a neutron is freed from a nucleus, the weak interaction of quarks will play the major role, and since the proton is lighter than a neutron, it is allowed for the neutron to go to this lighter stage by radiating out an electron and antineutrino. A free neutron is unstable and it decays with a half-life of about 11 minutes. Well, now you must be wondering, where does the neutrino fit into this history? In the 1930s, physicists observed that energy released in beta decay seemed to violate the conservation of energy. For example, carbon-14 decays by beta emission into nitrogen-14. Let's calculate how much energy is released in this process. To calculate the energy released in this process, we must find the mass difference before and after decay. Pay attention. We would expect the emitted electron to have a kinetic energy of 156 kilo-electron-volts, but the vast majority of emitted electrons have somewhat less energy. In 1930, Wolfgang Pauli proposed an alternate solution. Perhaps a new particle that was very difficult to detect was emitted during decay in addition to the electron. This new particle could be carrying off the energy, momentum and angular momentum required to maintain the conservation laws. This new particle was named the neutrino by Enrico Fermi. The neutrino was first observed in 1956 in Los Alamos National Laboratory. Neutrinos are difficult to detect experimentally because they are uncharged particles with almost no mass. Also, neutrinos interact very weakly with matter, so they are very difficult to detect. Now would be a good time to discuss proton decay. Beta plus decay can occur from some unstable isotopes that have too few neutrons to be stable. A proton in the parent nucleus decays into a neutron that remains in the daughter nucleus, and the nucleus emits a neutrino and a positron. Electron capture occurs when there are too many protons in the nucleus. In this case, one of the orbital electrons is captured by a proton in the nucleus. This creates a neutron and a neutrino which is emitted. In both, the neutron remains inside the nucleus. Beta plus decay and electron capture, forms of radioactive decay which see a proton become a neutron, are not proton decay, since the proton interacts with other particles within the atom. A free proton from a nucleus is stable and it is very simple to understand. The proton is the lightest of the baryons. Baryons are particles made up of 3 quarks. In particle decay, the total baryon number before an interaction has to be the same as the total baryon number afterwards. Since proton decay violates the conservation of baryon number and the conservation of mass, protons are very stable particles. The mean life for protons is approximately 10 to the power of 33 years.